Hi guys, in this video I'll be doing step-by-step derivation to calculate the true conditions of four sentences that is seen in semantics. I'll be using a Hyman-Kratzer notation to do so. I've written the logical forms of each sentence, as you can see. I've written the syntactic trees of them, and this is because drawing syntactic trees is not the scope of semantics, it is rather the scope of syntax. So to gain us some time, I've done this already, and what we're going to do in this video will be to assign types to each one of the nodes and to learn about do some exercises about function and function application, predicate modification, predicate abstraction, as well as PTR. So I'm assuming that you're familiar with the combinatorial rules, because this video is not an introduction, it's just going to be solving some exercises, and I hope it goes well. But before we get into our examples, which will go, by the way, gradually more difficult, so the first example is the easiest, and the fourth one is the most one, and it's the most difficult one. Before we get into our examples, what I want to do is to introduce briefly, introduce the combinatorial rules briefly. We have three combinatorial rules. The first one, and the one that we're going to use the most, is function application. It's the easiest one. So in function application, we have, for any assignment function A, by assignment function A we mean a domain. So for any assignment function A, when alpha is the mother, such that alpha is a complex expression, and it has daughters b, beta, and theta, such that b denotes a function, for example, e, t, and t is the argument of it. Then the notation of alpha would be b, such that b takes t as the argument. It looks like this. The next one is predicate modification. When we use predicate modification, we use predicate modification when both the mother as well as its daughters are of type ET. So for any assignment function E, if beta and theta are functions of type ET, and also their mother is also of type ET, so then the denotation of the mother, which is alpha, would be lambda x, such that bx and tx denotes 1. Bx denotes 1 and tx denotes 1. Something like this. Yeah, the denotation of alpha is really important because we use and in here. Because normally in function application what we have is an argument. One of them is an argument, another is the function. I mean, theta could also be, the argument could also be a function, but one of them takes the other, one of the sisters takes the other sister as its input and returns their mother. But in predicate modification, each and every member of these three nodes is of type ET. They're all of type ET, and the denotation of the mother is important in that it denotes lambda x such that bx denotes 1 and tx denotes 1. Our last combinatorial rule is predicate abstraction. Predicate abstraction is used when we have an indice, a natural number, in our syntactic tree, in our logical form. So for any assignments A, the denotation of alpha, which is the mother, such that it has beta and a natural number as its daughters, when this happens, the denotation of alpha is lambda x, such that B is in the domain A, such that A maps n to x. In the domain A, the natural number n, which is in the logical form as well, will be mapped to x. This x in lambda over here, the very same x in our lambda. When we use a predicate abstraction, usually the next step will be to use pronouns and traces rule. Now, something to note is that PTR is not a combinatorial rule, but it's something that we will really need to make use of, so let's talk about it as well. Pronouns and traces rule is, so when we have a predicate abstraction, what we have is something like this. In the assignment function A, n is mapped to x, we say, right? So if you give it n as the input, it'll return x, because the domain of the assignment function A maps n to x. So if you give it n as an argument, then it'll return x. But what if you give it, so this very calculation is called PTR. This is how we do it. What we do essentially is to write down a n, and n maps to x. We're gonna see many examples of this, so I'm not gonna get really, I'm not gonna give you a detailed expression for now. But if we gave it m as the input, it would just return the same thing, to be honest. It would look like this. It wouldn't be an actual entity like x is. So this calculation is done thanks to PTR, and we assign this domain the mapping thanks to predicate abstraction, PA. Now that we know all of this, we can now get right into calculating our true conditions for exercises. The first exercise that we have is Hall loves Sophie. So here's our logical form. Here's our syntactic tree, and we just start off. So what we do when we're calculating true conditions is to assigning types to each of the nodes. And then the next step is to determine which combinatorial rule I'm going to need to make use of to calculate each of the denotations of the nodes. So first of all, what I know is Hall is an entity, which is of type E. Entities are of type E. Truth values are of type T. So the whole sentence will denote a truth value, therefore it is of type T. Sophie is also an entity of type E. And loves, I know, is, thanks to my lexicon, I know that love is a two-place function, a transitive verb, taking two arguments and returning a truth value. Therefore, we can say that it's of type EET. Since we're calculating true conditions, this means that we are calculating what we need in a particular universe for the sentence to be 1. Because there are two possibilities. It is either 0 or 1. For the sentence to be true, I'm going to calculate what conditions that we're going to need in this world. So truth conditions are not definitive. They're going to tell you what we need for the sentence to be true, but they're not going to tell the exact truth value of the sentence. To know the truth value of a sentence, we would need real life knowledge, which we don't. And by the way, I just realized that I wrote this wrong. Okay. Now that we have assigned our types, let's there's this one as well. So this predicate transitive verb, loves, is a function of type EET. Therefore, it takes two arguments, and the first argument it takes is Sophie. It is taking Sophie as input, and it's going to return a function of type ET, which goes over here. And in this very part, we take Hall as the argument, because Hall will be taken by this function, by its sister, and then which will then return a truth value. Okay. Now that we have assigned our types, let's just see what combinatorial rules that we're going to need to use. For the reasons I've explained just a minute ago, we're going to need to use FAs, because these are just basic function applications, right? I just start off by writing my sentence, which is Hall loves Sophie. First step, so we're here right now. This is my sentence, Hall loves Sophie. And to get over here, I'm going to need to factor out Hall. As you see, I'm going to separate and factor out Hall. To do that, loves Sophie would have to be the function, because as you can see, it is the function. The loves Sophie is the function, while Hall is the argument. Therefore, I'm taking Hall as the argument. Entities are written in denotation brackets, the double brackets, as you can see over here. This is the result I got. I've calculated thanks to FA. By FA. Now, what I'm going to need to do is to factor out Sophie, because it is the argument, while loves is the function, so I'm leaving loves alone. And I'm factoring out Sophie, which is another entity. So Sophie here, Haku here. As you can see now, I have my predicates. I have two of my arguments. The first argument that is next to loves is Sophie and not Haku. This is because loves and Sophie are adjacent to each other in my logical form. What the predicate loves does, is to connect with Sophie first, and then it connects with Hall. So Sophie comes first, which is the object. The object comes first, and then the subject. in my logical form, because this is the first function. And it is right next to Sophie. It's sister to Sophie. So this was also achieved by function application. Now, something to do is to search for the meaning of laws in my lexicon. For the predicate laws, as we know, is a two-place function. It takes two arguments and returns x laws y. So since it has two arguments, I'm gonna need two lambdas. Lambda x, lambda y. You can assign any letter to them. It doesn't matter, but we usually start off with x, y, z, r, something like this. So since it has two predicates, I'm just saying, sorry, not two predicates, but two arguments. I'm saying lambda x, lambda y, such that y allows x. Why did I say y allows x? Because first of all, laws is connected with Sophie. So Sophie would have to be x, because in my denotation I have written lambda x first. So x is Sophie because laws connects with Sophie first. And next up comes lambda y. So when you look at the sentence, y allows x. This is why. The reason why I didn't say x allows y and instead I said y allows x is because first of all, in my denotation I'm writing x, lambda x, and the first lambda that needs to be eliminated, calculated, let's say, would have to be Sophie because they're sister. It is sister to the first function that I'm gonna computate. So yeah, now I also need to write down my arguments, which is Sophie and Haku. Here we go. This was thanks to my lexicon, so this was calculated by lexicon. Now, all we need to do is to eliminate lambdas. For lambda elimination, we take a look at our brackets, which is over here. And the first lambda that I come across in my brackets is lambda x. And right outside of the brackets, right on the right of my breakfast. Breakfast? What? What do you mean breakfast? Okay, on the very right of my bracket, I have Sophie. So Sophie comes first. Sophie will eliminate lambda x and get in the place of x. Therefore, I get lambda y such that y allows Sophie, because instead of x, I'm writing Sophie. Since Sophie eliminated lambda x, I'm writing Sophie instead of x. Now I still have one more argument, which is Haku. So here we go. We did this by lambda elimination. Now, again, I'm taking a look at my brackets, and right inside of the brackets we have lambda y, which will be eliminated by the first argument that is right next to my bracket, ending bracket, which is Haku. Haku will get instead of y, because Haku will be eliminating lambda y. Therefore, I can say that this sentence, my first sentence, Hall loves Sophie, denotes 1 if and only if Haku loves Sophie. Again, this was thanks to lambda elimination. So here it is, the truth condition. Here is the truth condition of our first sentence. Hall loves Sophie denotes 1 if and only if Haku loves Sophie. This is how we supposedly compute the sentences in our brains to make the meaning of it according to Heim and Kretzer notation. So the thing about it is that the reason why we say 1 if and only if is because this sentence wouldn't be definitive. Maybe Hall doesn't love Sophie in some universe. So Hall loves Sophie denotes 1 if and only if Haku loves Sophie. Yeah, because if it was a truth value, you could say Haku loves Sophie, but it is not a truth value. It is a truth condition. The condition of the sentence for it to be true, to denote 1, is for Haku to love Sophie. So it's not definitive. I have to say 1 if and only if. And we could also say Hall loves Sophie denotes 0 if and only if Haku doesn't love Sophie. This would also hold true in this very universe, in some universe. Our next example will be Kiki is an adventurous young witch. Kiki is an adventurous young witch. Here's the logical form. And for this sentence, you see that is and an are in brackets, and the reason for that is because I am not including them in my logical form. I'm also not including them in my semantic solution, and this is because they're only there to serve a grammatical purpose. They don't actually have a function in semantics. Because as you can see, these have context. These have content, while is and an do not have a content. They're there to serve a grammatical purpose and not a function. And they're not an entity, they're not a truth value, so they're not a function, they're nothing. They just serve a grammatical purpose, so I'm not including them at all. Okay, again, the first thing that we do, as always, is to assign types. So the whole sentence would denote... so which pen should I go with? I'm gonna go with, I don't know, this one. Whole sentence denotes T. Whole sentences of type T. Kiki is an entity of type E. And here I have two adjectives, adventurous and young. Adjectives are of type ET because they take an entity and they return a truth value. Young as well, it's also an adjective. And a non-predicate such as which. Kiki is a which. When we say that, it also denotes, it is also of type ET, a function of type ET. And the reason for that is because it takes an entity, just like adjectives, it takes an entity and it returns a truth value. It takes Kiki as its argument and it returns 0 if Kiki is not a which, and it returns 1 if Kiki is a which. So this is the way it is. These are our types. Now the next up, we're going to take a look at these nodes. Let's start with this one. So I have E as the argument and T as the outcome. Since input is T, I'm writing it over here, and this node would have to be of type ET for it to take Kiki as its argument, which is an entity, and return a truth value. And next up, this very node. As you can see, both of its daughters are of type ET. So this adjective young needs an entity to take as the input, but we don't have an E as the input, so which also needs an entity to take as the input, but its sister is not an entity. Therefore, what I can say is that they cannot take each other as inputs. They're of the same type. They cannot take one another as the input. Therefore, we need to use predicate modification, and their mother would have to be of type ET. Remember predicate modification. The denotation of this very node would have to be lambda x such that B, which is of type ET, theta, which is of type ET. Okay. The denotation of alpha, which is their mother, would be lambda x such that Bx denotes 1 and Tx also denotes 1. Okay. Now, which combinatorial rules am I going to need to use? Let's take a look at that as well. So for the first calculation for this node, I'm going to need to use function application. It's just basic thing. This is predicate modification for the reason I've explained. This is also predicate modification, which I have written already. With these at hand, let's start off by writing the whole sentence. Let's write down the whole sentence looking at my logical form, which is Kiki, adventurous, young, which. I'm not including is or an. Kiki, adventurous, young, which. The first thing I need to do is that take Kiki as the argument, therefore factor out Kiki and use this part as the function. Therefore, this node denotes adventurous, young, which takes Kiki as the argument. Thanks to FA, by FA. Next step will be to use predicate modification to factor out adventurous and young which, like separating adventurous and young which. Okay, the formula of predicate modification. So since I'm trying to write the denotation of their mother, what I would need to do would be to use lambda calculation. So I'm starting off strong with lambda x such that b, in this case it's adventurous. I'm taking adventurous as the function. Bx denotes 1. I'm just applying the formula that you see over here. And theta, which in this case is young witch. X denotes 1. And then I'm closing my brackets. I also have Kiki as the argument. And this was done by predicate modification. Okay. Next up, I'm gonna need to use predicate modification to separate young and witch. And to do that, I'm gonna need another lambda calculation, and this calculation will be done on this very part. The remaining part will look the same. Lambda x adventurous x denotes 1, and so I'm dealing with the part that is young witch. This part separated. So what I need to do is open a new bracket and start off with another lambda calculation, which for this one, I'm going to say lambda y, such that young y denotes 1 and witch y denotes 1. Since I've written this part, I have to write down the remaining bit as well, which is taking x as the argument denotes 1, and then I have the argument Kiki. So what I did for this young witch and to write it like this was to use predicate modification. I've just applied this formula to express this node as the alpha, and this bit as the beta, this bit as the theta, and I used predicate modification basically. So yeah, now that I've done now that I've applied all of the combinatorial rules that I needed to apply, what I should be doing now is to eliminate all of the lambdas to get the truth condition. So when we're eliminating truth conditions, what I like to do is to start off with the smallest little bracket. I have two brackets, the one here and the other here. I'm starting off with the smallest one because otherwise starting off with the big one causes complications when we have complex sentences. Well, maybe not this one, but we would definitely, if we're not super careful, we would definitely have some problems in an example like this one, because I did before a few times. So what I do is I start off with the smallest brackets, and write the remaining part as it is, the same way. And for this one, for this bracket, I'm gonna need to eliminate lambda y, because this is the first lambda that I come across in this brackets. Lambda y will be eliminated by x, which is the closest to my closing denotation bracket. X will eliminate lambda y, and instead of y, I will now be writing x. By the way, I've just realized that I forgot to add x over here. So there's another x. Not x, sorry, another y. Because of the formula, I just forgot to write it down, because normally after both of the denotations, you have to write the same whatever lambda you used, so my bad for that. Let's eliminate it. Since this lambda is eliminated, I no longer need to write the colored brackets, because there isn't another lambda in them. So what I do is I write young x denotes 1 and which x denotes 1, close the brackets. I also have arguments Kiki out there, so this was done by lambda elimination. Let's take a look. Lambda x adventurous x, lambda x such that adventurous x denotes 1, and young x denotes 1, and which x denotes 1, and I have the argument kiki. So I'm gonna need to do another lambda elimination as always. I'll be eliminating lambda x, see the brackets, I have the argument kiki. Instead of x, I'll be placing kiki. So let's go ahead and do just that. Adventurous kiki. What was that? Normally, when we're writing entities, we use double brackets for the arguments like this, but for ease of writing and to gain us some time, I'm no longer going to be using double brackets, but you know they're supposed to be there. I'm not going to be using double brackets for arguments now from now on, because normally kiki would have to be in double brackets, but it takes so much time to write that down. Alright, now the sentence that we have is adventurous kiki denotes 1 and young kiki denotes 1 and which kiki denotes 1. This was done thanks to lambda elimination because as you can see we've eliminated lambda x finally. And yeah, now we have the now we can finally derive the true condition of the sentence. Thanks to our lexicon, I know that if adventurous takes the argument kiki and denotes 1, it means Kiki is adventurous, Kiki is adventurous, Kiki is young, and Kiki is a witch. Therefore, this sentence denotes 1 if and only if Kiki is an adventurous young witch. So here it is, the truth condition of this very sentence using predicate modification is the second sentence denotes 1 if and only if Kiki is an adventurous young witch, and Kiki is an adventurous young witch denotes 0 if and only if Kiki is not an adventurous young witch. So to calculate this, what I did to summarize was to assign types, which I know that adjectives are of type ET and non-predicates are also of type ET, therefore I assigned them. And as you can see, when mother and both others are of type ET, we need to use a predicate modification to calculate it. And the denotation of the mother would be, let's call the mother alpha. The denotation of alpha would be lambda x such that beta x denotes 1 and theta x denotes 1, beta and theta as its daughters. So yeah. And then after I was done with predicate modifications, all I had to do was doing lambda eliminations as well as on the last step, making use of my lexicon. So here we have the denotations of these as well. Now our next example, our next sentence says, he introduced him to her. So this is very new to us because we have never had pronouns before, and these pronouns have indices attached to them. As you can see, these are called indices. And now we have a domain A. Domain A maps 1 to whole, maps 2 to Casper, and 3 to Sophie. So therefore, I know that this sentence would have to mean whole introduced Casper to Sophie. By the way, one thing to notice that indices don't have to go the ordinary way. Like I could have assigned 32 to he and 11 to him or 3 to her. Like it didn't have to be 1, 2, 3. It could be any number. Indices can have any number. In a domain, we don't have to go the ordinal way. Like the ordinary way is what I mean. So here's our logical form. He introduced him to her. Pronouns are entities of type E, obviously. The remaining bits are as well. The whole sentence denotes a truth value, therefore this very node would have to be of type ET, and we would need to calculate it using function application. And since this node denotes ET and it has E to take as the argument, this node takes E as the argument and returns a function of type ET. So it goes like this. This node takes E as the argument, which is here, E as the input, and returns ET as the output, as its mother. So now, to calculate this, I would have to use function application. And lastly, here we have E as the input, therefore introduced has to be a long function. It introduced takes E as the argument, it then returns its mother, which is of type E, E, T. So introduce is a three-place function. It has three arguments here. Therefore, first argument, him, second argument, her, and third argument, he. This is also calculated by FA, but one thing to note is that when we have indices, as I have explained before, when we have indices, predicates and traces rule would have to be applied to get the meaning of the indice, making use of our domain, making use of our assignment function A. What happens when we have an indice is that alpha is a pronoun or a trace. Assume that alpha is a pronoun or a trace, such as, in this case, it's a pronoun, with n is an element of natural numbers, such that it has this natural number n called its indice. In the domain of A, the denotation of alpha with the indice n in the domain A would be the assignment function A taking n as its arguments. So for example, if I wanted to calculate the meaning of he one, alpha refers to the pronoun, n refers to the indice, which in this case is 1, in the notation brackets, in the assignment function A, which is written in superscripts because domains are written in superscripts. Then the denotation of he would be, in the domain of A, the domain of A takes n, in this case it's 1, as I said, as its argument. And we would simplify this by looking at what's A maps 1 to what. So I'm taking a look at the assignment function A, and it maps 1 to whole. Therefore, by simplifying this, I would get the meaning whole. Something like this. It's easy. It really is easy. Now, as always, I start off by writing my whole sentence. He one introduced him to her. The first thing that my function, that my predicate does, is to connect with him, taking him as its argument. So one thing that I need to do, the first thing, no, we're starting off from here because we're here. This is a T. Sorry about the confusion. So since this refers to the T, this whole sentence, this denotation refers to the T, what I need to do is to factor out he. Factoring out he, I get introduced him to her. Also, this is in the domain of, because see, the assignment function A is here, takes he one as its argument. It's also in the domain A. Next up, the next argument it takes is her, to her. Before doing so, let's just note then that we have done this by FA, function application, because we have done this FA and now we're in this node. We need to calculate this node and we are factoring out to her. So we're left with introduced him to, in the domain A, to her, in the domain A as well. Lastly, he, which I have factored out first. It's also in the domain A. This was again thanks to FA, by FA. Now that I'm in this node, let's calculate the denotation of it as well. What I need to do is to factor out him and leave introduced all alone, because it is the main function, and the rest are all entities, the arguments. Introduced, I no longer need to write it in the domain of A, because there's no such thing as introducing in the domain of A. It only has the three entities, so I'm assigning this domain as the superscripts of my pronouns, and not the verb, not the predicate. Introduced him to, in the domain of A, and I just need to write the rest, but I'm not going to. I'm just going to copy paste it. This was also done by, oh my god, sorry. This is also done by FA. Okay, now that I've done, I've applied all of my combinatorial rules, I've used all of the combinatorial rules that I needed to use. What I need to do is to search for the meaning of introduced in my lexicon. And what I also need to do is to apply PTR. Which one to do first would be right? I'm wondering. I think that's, well, I'm not sure at all, but which one should we go with first? I think using PTR would be much faster for this step, for us to go further. So I'm just going to write introduced again. And when we see him like this, the notation of it is the assignment function A taking 2, which is its index, as the argument. And for this one, in the domain A, we take the argument 3, the index 3. And for this one, it would be like this. We have 3 arguments. We have done this by PTR. And by simplification, what I can do is to take a look at this domain, the assignment function A, the domain A, and assign the names to my indexes. So introduced to the assignment function A maps 2 to Calcifer. It maps 3 to Sophie, and the domain of A assigns 1 to Hall. So therefore I have all of my arguments now. Now the last step is to search for the meaning of introduced. In my lexicon, what I see by taking a look at the type of introduced is that it takes 3 arguments. So taking 3 arguments means I need to assign 3 lambdas to the meaning of introduced. We have lambda x, lambda y, lambda z in order. You can assign any letter, but it's easy to order x, y, z, and then r, if you need more. So we need to say this introduced this to this, but how do I know which is which? How do I know which x is? I look at the logical form that I have and see that introduced matches up with him. So I assign x to him, and then this whole thing, this very node matches up with her, is sister to her. Therefore, I'm assigning y to her, and finally z to he. So the denotation of introduced by making use of my lexicon is lambda x, lambda y, lambda z, such that z introduced x to y. The reason why I didn't say x introduced y to z, and instead I said z introduced x to y, is because the first thing that I've written here is lambda x, and the first thing that the predicate introduced is sister to is him. So I assigned x to him, y to her, which is the second one, and he to z. And then I just typically write my arguments as well. This was thanks to my lexicon. So yeah, all we need to do is now do lambda eliminations, and it's really easy. I take a look at my brackets, and the first lambda we have is lambda x, and the first argument that is right outside of the brackets, on the right of the brackets, is Calcifer. So I'm assigning Calcifer to x, and therefore I'm saying lambda y, lambda z, z introduced Calcifer to y. I have 2 more arguments, Sophie and Hall. Also, this was by lambda elimination. And now inside of my brackets, what I have is, also let's just use this one, lambda y, and on the right of the brackets we have Sophie, so lambda y will be eliminated by Sophie, and instead of y I'll start writing down Sophie. So lambda z, such that z introduced Calcifer to Sophie. And I have one last argument, which is Hal. This denotation was also written by lambda elimination. Alright. Now these brackets have lambda z in them and Hal right outside of it. So Hal will eliminate lambda z, and instead of z I'll start writing Hal. So this whole sentence denotes one, if and only if Hal introduced Calcifer to Sophie. He introduced him to her, denotes one, if and only if Hal introduced Calcifer to Sophie. Now that we're done with our third example as well, let's take a look at it and summarize it real quickly. The first thing that I did was to assign types to them. I assigned to my pronouns e, which because they're entities. Introduce takes 3 arguments, 1, 2, 3 arguments, and returns a truth value at the end. And the first entity that it meets is him, and second one is her, and the last one is he, basically. So I assigned each one of these letters to them because there are 3 entities that introduced needs to take. And what I did was to do apply function applications all over. And the next step, I was met with these domains and indices, and to get rid of my indices, I had to make use of PTR, predicate and traces rule. So I did that by writing the domain and taking whatever is the indice as the argument, and then I simplified them and made use of my domain assignment function A. So then I had the whole sentence. I made use of my lexicon to write down the meaning of write down the denotation of the predicate introduced. Introduce is a three-place function which takes obviously 3 arguments, x, y, and z. So then I had to do lambda eliminations to get the truth condition of our third example. So yeah, he introduced him to her denotes 1 if and only if whole. He introduced Casper to Sophie in this very domain, in this very universe. So yeah, we're done with the third example. Now let's move on to the fourth one. And I'm really excited to do this one because it's really the most fun one. And we have some things that we have never covered before. You might have obviously seen them before, but we haven't mentioned them in this video, so they're new to this video. So let's take a look. First of all, in the sentence, Haku is a white dragon who helped Chiro, I have is and a. For the same reason as this one, is and an are not mentioned in my logical form. And this is because they only serve a grammatical function. They only serve a grammatical purpose. They don't have a function. Yeah, so the first thing that I do, as always, is to write down my types. And I do so real quick. I'm going to be using this. So the whole sentence is a truth value, therefore it is of type T. Haku is an entity of type E. Chiro is also an entity of type E. Yeah, white is an adjective of type ET because I know that adjectives are of type ET. Dragon is a noun predicate, and noun predicates are of type ET as well. Here I have 2 daughters of type ET, therefore their mother would have to be of type ET as well, and I would need to apply predicate modification over here. So let's go ahead and do just that. Predicate modification. And what about this node? This node would have to be of type ET to take Haku as the argument, as the input, and return T, therefore it is of type ET, I can say, and I would need to apply function application here. And then, so who is new to us? This is a related clause. Haku is a white dragon who helps Chiro. Who is an operator? And operators are always of type ET. This is something to memorize because the way that it works is who takes whatever has come before, and it will be returning whatever is up there. It's serving a grammatical purpose, but it also is a function because it does have a semantic function as well. Not only semantic, but also syntactic resolution had to be done. So this is its type. Who is of type? Sorry, what am I doing, guys? Who would have to be of type ET? Alright, now, what about its mother then? Well, I don't know what its mother could be, so let's take a look at down there. Help. Help is a two-place predicate because, as you see, we have 2 arguments here, Haku and Chiro, so therefore it would need to take 2 E's, 2 entities as its arguments, and then return a truth value. Therefore, the denotation, helped is helped is a function of type EET. Therefore, their mother, which is this node, what would have to be? It would have to be, well, it takes E as the argument and it would have to return ET. Here we have it. Here we have T2 also. There's actually a 2, but I didn't write it for some reason. I think I deleted it, erased it by accident. Anyway, this is a trace. Traces are... So basically, this is the trace of Haku. Haku used to be there. This is for syntactic reasons. there had to be a movement for Haku to move up, because to satisfy EPP. But again, this has to do with with syntax, and it's not the scope of semantics, so I'm not going to mention it very much. To briefly explain, Haku used to be there. It's left, and it's Haku left. It's index, which is 2 over here, right on top of it, right atop the trace. To satisfy EPP, it's moved up. This is what it did. And the reason why Haku had to be there was because Haku is a white dragon. Haku helped Chiro, so to not have two Haku 2 times in this sentence, we moved it up. And here Haku left a trace, so we can say that traces are always, just like pronouns, traces are always of type E. And by the way, indices do not have a type. They never have a type. Anyway, the mother of this one would have to be, since this is taking E as the argument, it will return T. What's going on? We've never had a T in the middle of our logical form before. What we need to do is see the indice here. Remember the predicate abstraction rule. When we have an indice, a natural number in our logical form, to deal with it, we had to make use of predicate abstraction. Basically, when we see something like this, such that alpha is the mother, beta is the daughter, and the other daughter is n, such that n is a natural number. When we see something like this, the denotation of their mother would have to be lambda x, such that beta in the domain of A denotes n, which is the indice, which is also its sister, to x, or lambda. You see, this n is the same as this n, the indice that we have. So this is basically how it goes. Predicate abstraction is like this. What we can say is when we have an indice like this, its mother has to be of type ET. We need to use a lambda here because of predicate abstraction. So what I can say is that we need to use predicate abstraction to calculate this one. Also for this one, we use function application. It's just basic. This one is also function application because Chiro is the argument, help is the function, and it returns ET as its mother, which makes perfect sense or something. Anyway, last node that I need to mention is this node. Let's take a look at it as well. So we have who and ET as its sister. So ET is taken as the argument, the input, and the output would have to be ET. Okay, now what other combinatorial rules do I need to use? Let's take a look at here. I see 2 ETs, therefore this is predicate modification. And here I see just our usual function application because ET is taken as the input and the output is their mother. Makes perfect sense. We have so many FAs and so many PMs, so for the steps to be easier, I'm just gonna give them numbers. This is not something that Hyman Kratzer suggested, I don't think so, no. But this is something I use to make the whole calculation easier to follow, for the steps to be easier to follow. So I'll call this FA1, FA2, FA3, FA4, PM1, PM2. Because remember, I write our calculations like this, and to follow the steps, this will make the whole process much more easier. Now that we have assigned our types, and we have also determined which combinatorial rules that we're gonna need to use, we can finally start calculating our truth conditions. Okay, the first thing I do is to write the notation of T, the whole sentence. By looking at my logical form, I need to write Haku, white, dragon, who to T2 helped, Chiro. Right? Now the first thing I need to do to calculate the next function, which is ET, which is a function of type ET, I need to factor out Haku, and to do so, let's do it. The function is this part. The argument is Haku. Therefore, let's start off by writing the function first. White dragon who to T2 helped Chiro with the argument Haku. Haku would be in double brackets, but I'm not doing it because I'm gonna need to write Haku so many times. This sentence has so many steps, so I'm not gonna use double brackets. But just assume that there's double brackets. for Haku. Okay. Now that I've factored out Haku by function application, I can move on to my next step, which is predicate modification. This predicate modification will separate two elements. First one is white dragon, here. Second one is the rest of the sentence, which is who Tuitu helped Chiro. Okay. Remember predicate modification, I need the lambda x such that the first bit is white dragon, x denotes 1, and who T2 helped Chiro, x also denotes 1, because the brackets, we also have the argument Haku. So this was by predicate modification. Okay, now that we've done this, let's take a look at our next step. So I could either go this way or this way, but this one will be much more short to make. It will take much less time to calculate this one, so I'm going with this one, but you can go the other way around. It's up to you, but I'm just going to go with this one because it's easier and it's going to take less time, as I said. Anyway, to calculate, to separate white and dragon using predicate modification, what I'm going to need to do is to deal only with these brackets, in these brackets, and the rest will look the same. So what I do is lambda x, write down lambda x, and I'm dealing with white dragon only, because this node only has white and dragon as its daughters. So I open up new brackets and I'm going to use a new lambda because predicate modification requires lambda y such that white y denotes 1 and dragon y also denotes 1. Close the brackets. So this part, lambda y such that white y denotes 1 and dragon y denotes 1, is the denotation of white dragon, and the remaining part, which is this whole part, will have to be written all the same. To make it faster, I've just copied it. And this was also done by predicate modification that is seen over here. So let's write that down as well. Okay, now next up, I'm going to need to calculate this node. And for that, I need to use who as the function and the remaining bit as the argument. That's right. But before getting into this, what I can do is also to simplify this whole situation here. I can eliminate some lambdas so that the whole denotation would be shorter. Let's just eliminate our lambdas, okay? So we see, let's start off with the smallest brackets that we have, which are this one, which is this one. And I have lambda y in here. Instead of lambda y, I'll be putting x. So x will eliminate lambda y, and instead of y, I'll be writing my x's. So lambda x such that I no longer need to write the colored brackets white x, because instead of y, I'm now putting x denotes 1 and dragon x denotes 1. And of course, the remaining part, which is who T2 helped Shiro. As well as my argument Haku. This was thanks to lambda elimination, Let's take a look. Lambda x such that white x denotes 1 and dragon x denotes 1. What I can say is that, well, there's a certain truth that making use of my lexicon, I can say that lambda x such that x is white, because the meaning of white x denotes 1 is x is white and x is a dragon. Using my lexicon, I turned this into this. and the remaining bits will have to be written the same way. Also, because this is you can write down and instead of this symbol. It is totally up to you. You can do both. And then the remaining bits again. Actually, let's change it. Let's take a look at our next step. Next step is FA2 to factor out who. Factor out actually this part, because this is the argument and who is the function that we're going to make use of. One thing about operators is that operators eat themselves up. As I've told you while explaining the logical form, what who does is to connect this with this. So it doesn't really serve an actual function like the rest of the nodes do. It's going to eat itself up. Making use of my lexicon, I know the meaning of who. Lambda p of type ET, which then returns lambda p. Therefore, it basically eats itself up. It has no purpose after this point, after I'm factoring out who. Like this. Actually, there's actually one extra step that I didn't mention. I assumed that you would understand, but let's write it down as well. Who is, as I said, who is the function, and it takes the remaining bits as its argument. Reason why this bit is the argument, although it at least seems longer in a logical form, is because of its type. Okay. Now, who takes 2t2 helped 0 as its argument. And I also have x, and I also have 1, something like this. And I also have haku, as always. Actually, not simplification. I use my lexicon to write down the first bit of it. To write this down, I used my lexicon. And then for this part, I did FA. Okay. Now, the meaning of who is searched in the lexicon and found out like this. This is something to memorize again. You don't even have to include the step because it's basically going to eat itself up. And in the next step, this will just be gone and the remaining bits will have no change in it. So let's write down the rest. And then who will be eaten up. And the rest, as I've said, is the same. This was thanks to our lexicon. Okay, next up, to the operator who after the operator who ate itself up. Now what I want to do is to do predicate abstraction, because this is the next step. I'll get rid of the innice too. I'll deal with it. So the first part, as you see, is always the same. Now, because this piece is set, and I'm just dealing with the remaining part, which is this bit. So from now on I'll be copying this part, which refers to this very part. Anyway, now we're gonna use predicate abstraction by assigning a domain. What's gonna happen is we have 2t2 help 0 here, 2t2 help 0, and to make use of my predicate abstraction, remember the formula we have in the lambda, but I have already used lambda x, so this time I'm writing lambda y such that I'm not going to include index because I'm going to write it in superscript, so I get rid of 2 for now, and I write t2 helped 0 like this, t2 helped 0, and it is in the domain of a, assignment function a, 2, which is my index, is mapped to this lambda I have here, 2 is mapped to y. This is my domain now. Index is moved to the superscript part. Index that used to be here is no longer here. It's moved to the superscript as the domain. This will be my mapping. So to t have 0 with the domain 2, which maps 2 to y. And then I have the remaining part of the sentence, which is I have x minus 1 and close brackets. I have haku as well. Okay, what we did here was that we made use of predicate abstraction. Okay, now for our next step, let's just start off by writing the first part first bit first. What am I saying? And the next step, now that we are done with our predicate abstraction, next thing that we will need to do will be function application tree. Function application tree. Okay, to move along with it, to make this real, what we need to do is, as you can see, the trace t2 is taken as the argument and the remaining part is taken as the function. So t2 will be the argument and the remaining part will be the function itself. We will be factoring out t2 basically. So I'm writing this bit the same, lambda y, because I'm dealing only with this part and I'm factoring out t2. I'm taking t2 as the argument now, the remaining part, which is helped chiro remains like this, and t2 will be my new argument, and the domain, this domain will be the superscript of my trace. T2 has the domain 2 mapped to y like this. This is my new argument now. I have factored out t2 successfully, and I will now be writing down the remaining part. This was done thanks to FA3. Okay, now in the next step, write down the first part again. I'm going to be doing function application 4, and I'll be factoring out chiro for this one. Because as you can see, chiro is the argument and helped is the function itself. Therefore, I'll be factoring out chiro. But before getting into that, maybe we need to simplify this because it's looking a little confusing. And after PA, as I told you, the next step is usually PTR, because this 2, the indice 2, will need to be mapped to something. Okay, let's take a look at it. Again, lambda y. Yeah, I'm factoring out chiro, and because of that reason, chiro will be the arguments now, like this. And I have this very argument. I'm working on this as an extra step, because I don't want to write it down again and again and again. Let's deal with it already. What happens for PTR is that I write down the domain, which let's call it A. You can call it anything, but I'm going to call it A because it really doesn't matter at all. What you call it doesn't matter at all. So let's call it A. It will be mapped. A has the domain 2 to y, right? And we give it 2 as the argument because you can see our argument was 2. So then close it. In the next steps, this will be turned into, if you give the domain A, which maps 2 to y, the argument 2, then obviously it is going to return y2 because you gave it 2. And the only job that the domain, the assignment function A has, is to return y when it takes 2 as its input. So obviously it will then return y. Actually, to explain about it to you, I'll just do something like this. This returned to this one, and this then turned into this one. And for the remaining part, I'm writing it the same way. For this first step, what I did was to factor out chiro. Therefore, I did my last function application. And I also made use of PTR here. And now I will need to do simplification. By simplification, this thing will turn into y. But this is the job of the next step. So, for our next step, guys, take a look. We have done everything. We did FA 1, 2, 3, 4, 1, 2, 3, 4. We did 3 predicate modifications as well as PA, and as we went along the steps, we also had to do PTR, and we made use of our lexicon at some points. And now, what should we do now? Let's simplify this a little bit. Actually, the meaning of helped, we need to write it down. So the meaning of help, let's take a look. Help is a two-place function. Therefore, it takes 2 arguments, which one of them is chiro and the other is haku, basically. So since it has 2 arguments, I'm going to write down lambda x. But I've already used lambda x and I've already used lambda y. So let's now call it lambda z and lambda r. This helps this, but who is z, who is r? Let's take a look. The first thing I've written was lambda z. So that means that the first thing that helped, the first argument that helped takes would have to be z. Chiro is z, haku is r. Because the first argument that helped, the predicate helped, takes is chiro, so therefore it has to be written this first, z and r, such that haku helped chiro, and I assigned r to haku, so r helped chiro, which is z. And, okay, I have chiro as the argument. Sorry, it just keeps moving. Chiro as the argument, and then we simplified this form into y. And I've written it before, but then it disappeared. I mean, I had to erase it to make chiro fit in there. So then I write the remaining part of the denotation. Lastly, I have haku as the argument, and this was done by our lexicon, as well as simplification. All right. Now, all I need to do is to do some lambda eliminations. So, as I told you before, what I like to do is to start off with the smallest denotations. We have a lot of denotation brackets in here. We have a lot of brackets, and the smallest bracket is this one, and then we have this one, and lastly we have this one. So I'm starting off with the smallest one. And as you can see, the smallest bracket, the first lambda I see is lambda z. So one thing I'm going to do is get rid of lambda z using the chiro. Chiro will eliminate lambda z, and instead of z, I'll now be writing chiro. Lambda y, lambda r, such that r helped chiro, and it has the arguments y, x, denotes 1, close the brackets. I also have haku here. So this was by lambda elimination. I almost said function application. Anyway, next up, in our smallest bracket, we have one more lambda, which is lambda r. This is the reason why I had to write the denotation, these brackets, because we still have a lambda in the bracket, so I wrote down the brackets again. So lambda r will be eliminated by y, and instead of r, I will now be writing y. The first part comes first, and then lambda y. I no longer need to write the colored brackets, and instead of r, I'm putting y. Y helped chiro. And it has the this one argument x denotes 1, and close the brackets, it also has haku. This was again done by lambda elimination. Now for our next step, what I'm gonna need to do is again write down the first part. And here we have in this little denotation bracket, sorry about that. Where is it? Okay, in this denotation brackets, I have lambda y, which comes first. Lambda y will be eliminated by x, and instead of y, I'm going to be putting x's now. X helped chiro. and then I have my last argument, which is haku. And the reason why I'm no longer writing this denotes 1 is because I expressed it in here, x help chiro turned into a sentence. Therefore, we understand that it already denotes 1 if x helped chiro. So this is the reason why I no longer write that denotes 1. So this was also done by Lambda elimination. And guys, we are at the last step finally. I'm so excited. I'm really, truly so excited because this is our finally last step. Here, this looks crazy. The whole steps all together looks crazy, especially for the last one. But here we are at the end track or something, whatever it is called. We have one more bracket, which is the biggest bracket, and in the bracket we see only one lambda, which means that we can get rid of the brackets, and lambda x will be eliminated by our last argument, haku. Instead of x, I will now be putting haku. Therefore, we can say that haku eliminated lambda x. And this sentence, guys, my first sentence, haku is the white dragon who helped Shiro denotes 1 if and only if haku is white and haku is a dragon and haku helped Shiro. Therefore, this sentence, the fourth sentence, denotes 1 if and only if haku is a white dragon who helped Shiro. Oh my god, I'm so excited. There we go. This was thanks to our last lambda elimination, as well as our lexicon. So here we go. Haku is a white dragon who helped Shiro denotes, according to our logical form, denotes 1, if and only if Haku is a white dragon who helped Shiro, and it also denotes 0 if and only if Haku is not a white dragon who helped Shiro. So yeah, this is all we had to do to get the truth conditions of the fourth sentence. Let's summarize what we did for this one. So we started off by assigning our types, which we assigned E for Haku and Shiro because they're entities, and for the whole sentence we assigned T as we always do. For predicates, for non-predicates as well as adjectives, we had to assign ETs, and its mother would also have to be of type ET. And here we learned about the operator who, which is of type ET. Therefore, both its sister and its mother would have to be of type ET. And when we see an indice with T as its sister, we now know that we need to use predicate abstraction to get the meaning of it, to get rid of this indice, to deal with this indice. And traces are also of type E. So yeah, this is how it went. We applied all of our function applications, all of our predicate modification. Sometimes we made use of our lexicon. And then when we were applying predicate abstraction, which is, where is it? When we were applying our predicate abstraction, we wrote down the domain in the superscript as the domain. In the assignment function A, 2 maps to y. The assignment function A maps 2 to y. So this is what happened. And then we had to use PTR to get rid of the 2, and we assigned the mapping 2 to y for the assignment for the domain of A, which takes 2 as the input, and then it will return y, because this is the only job it does. It returns y when it takes 2 as the input, therefore it just turned into y, like you see here. And then after our PA, the last step we had to do was to factor out Shiro, which is our last argument. And then we did that, and then we, making use of our lexicon, we wrote down the notation of helped. It's a two-place function, a transitive verb. We call it lambda z, lambda r, such that r helped z. And the reason why we assigned r to Haku was because it was the latest argument, because the predicate helped takes Shiro as its argument first. Therefore, since we wrote z first, we had to assign z to Shiro and r to Haku because it comes later on in our logical form. So after this step, things were all easy because all we had to do was eliminate our lambdas. And finally, at the last step, we had to make use of our lexicon. So this is how we calculate the truth conditions of our first sentence. Haku is a white dragon who helped Shiro. And I hope you enjoyed this video because I enjoyed talking about it. I'm not a teacher or anything. I just like semantics, and I really wanted to make a video of this because I don't know, it's just really fun, and I love semantics so much. So I hope you enjoyed this video so much, video as well. And if you have any questions, you can comment down below as always. So thank you for watching, and see ya.